Welcome to the next video in our networking series, where we continue our journey through the transport layer, and more specifically the continuation of lecture 3B, part 2, the lecture that would not die. Does seem like this one's going on a bit, but TCP is a very big and complex beastie, so not surprising that it's going to take a few lectures to go through this one. And the scary bit is that we're only skimming over the surface of TCP. When you start to look down into all the optimizations and variants that exist, yep, TCP is a very complex protocol. Okay, so before we start this lecture, just a quick review where we were up to. So we were looking at how packets are transferred using the TCP protocol. So what information within the TCP header are we using to ensure reliable communications between the client and the server? And we saw that really broke down into timeout, sequence numbers, and acknowledgement numbers. And by using a combination of all three, we can handle all those misadventures. We can handle all those unexpected scenarios where packets are perhaps received out of order or get lost or delayed, to ensure that data is passed up to the application layer correctly. We finished off the last lecture looking at this pseudocode, so now we're going to look at a few examples. We're going to look at some different scenarios where things go wrong. Okay, so we've got our sequence diagram, so we've got our client, we've got our server, time is going down. So our client wants to send some data to the server, so it will transmit a packet. That packet will have a sequence number, so the starting byte count of the data it is sending. An acknowledgement number, so we're not really going to look at this one in this scenario. So this is the acknowledgement number for data that was sent by the server. So in this scenario, all data is coming from the client, so you can ignore that basically. We have a push flag set to say, use this data, and here is our data string of 5 characters, just sending the string hello. So you can see that there's a slope to that line, so there's a certain amount of time for that communication to occur. There's some propagation delay across our network, but eventually it'll be received by the server. The server then will send back an acknowledgement packet, so it'll look at the sequence number, look at the length of the data, so add 5 onto it. So that's 3 to 7, so that's 23 to 27, represents the bytes in that string. So it'll acknowledge back 28 to say the next sequence number I'm expecting you ends E28. But unfortunately, for some reason, that packet gets lost. Maybe there's a sudden burst of EMI radiation and bits are flipped on that copper wire and that packet is corrupted. So it will fail its checksum check, for example. So the client is sitting here, he's going, well, I'll transmit the data and eventually a timeout will occur. So if this was the first packet, that timeout will be 1 second. So 1 second has elapsed, it hasn't received acknowledgement. So it'll trigger a retransmission. So it'll go to its transmission buffer, it'll grab that packet and retransmit it. So again, that packet will be transmitted across the network, be received by the server will get that, and it will detect that this is an old packet. So it'll look at the sequence number and go, hang on a minute, I have received everything up to E28. You're sending me a packet with a sequence number of E23. I've already got that one. So it'll just dump it. It'll drop it. It will not process it. But it will acknowledge it. So it will send back an acknowledgement to the client. So it'll again send back the ACK number it's sent back previously. Remember, the acknowledgement number is the server saying to the client, I have received data up to this byte count. So this is the next sequence number I'm expecting to send back. So there's no kind of explicit error code within this. There's no difference between this acknowledgement packet and the previous acknowledgement packet. And from the client's point of view, it doesn't know that there was a previous ACK packet. But eventually it will receive this acknowledgement. It will receive an ACK number informing it that that packet has been received correctly. So in this scenario here, we recovered from a lost acknowledgement packet through a timeout and a retransmission of our data. Okay, example 2. So with the TCP communication, the client and the server are not in lockstep. So the client doesn't send a piece of data, then stops and waits until it gets the acknowledgement. It can keep chucking packets onto the network as fast as it can, and it will process the acknowledgements as they come back, as it receives them. So it's a full duplex communication link. So it can transmit and receive at the same time. So you can see here we have another scenario. So we have now the client sending 2 packets. We have exactly the same scenario, sending the hello packet, but straight away it also sends another packet with the word you in it. For the hello string, these will be the bytes ending 23, 24, 25, 26, 27. So the next sequence number will be starting 28. So for this U string, it'll be 28, 29, 2A. Hexadecimal. We're counting in hexadecimal. So the acknowledgement number for this packet will be ending 2B. Okay, so those packets are received by the server. The server will send back acknowledgements, but the first acknowledgement packet is lost. So the packet containing the acknowledgement number ending E28, again, is corrupted. It's lost. We do not get it back on the client. So the client will sit there. It will be waiting for that timeout to occur, but it does receive this acknowledgement packet within the timeout. So a timeout has not occurred yet. It will receive the acknowledgement for the second packet. And the key thing to remember here, as I highlighted in the previous example, the acknowledgement number tells the client what byte count the server has received up to. So with this acknowledgement ending E2B, the server is telling the client it's received everything up to, but not including this sequence number. So this is the next sequence number it's expecting. So even though that acknowledgement is missing, that's not important. The client knows it must have received it correctly because it wouldn't have sent this acknowledgement number otherwise. If it didn't receive this packet, then it would be sending back the acknowledgement number ending E23 because it received up to this value, but it hadn't received anything beyond that. So it would say, what have I received up to? So it's receiving a block of data broken down into a series of segments. And as it receives those segments, it will increment that acknowledgement number to say, what have I received up to? So because it receives an acknowledgement number that includes the missing ACK1, again, the client is happy. It knows that everything has been received correctly. Again, it can delete stuff from its transmit buffer. It can mark those segments as being received because it knows it doesn't need to retransmit them. Okay, so in the first two examples, we had stuff where stuff got lost. So a packet was corrupted, for example. But sometimes in network communications, your packets aren't lost, they're just delayed. Perhaps the acknowledgement packets had to come back via a longer path due to the network changing, the routing within the network changing. So you still get them, but they are just delayed. They take longer than you think, so a timeout may occur. So how do we handle that scenario? And this is what this example here looks at. So again, we have our client and server time going down our sequence diagram. So our client transmits two packets, hello you, and these are received at some point by the server. But however, the acknowledgements, you can see the slope is a lot steeper here. These acknowledgement packets down the bottom here don't arrive on the client before a timeout has occurred. So timeout will occur. So the client sends these packets, it then starts that timeout, doesn't receive anything, doesn't receive those acknowledgements by the time the timeout occurs. So it'll retransmit the oldest packet, as you can see here. So it's retransmitting the hello. So the client will transmit that packet to the server, it will restart the timeout, it will double that timeout. Remember, normally the timeout value is generated from an estimated RTT combined with a deviation in the RTT. But in the event of a timeout, that timeout value is doubled, just to make sure that we weren't being too optimistic, to give that server a little bit more time to respond if it's starting to get overloaded, for example, too much processing on that particular server, delaying its communication responses. But as you can see here, so we restarted that timeout, but then we get those acknowledgements eventually. So from the client's point of view, it's perfectly happy. It's got back an acknowledgement number here telling it what the server has received up to. So ending E2B, it knows that these two packets have been received okay, so the world is good from its point of view. Equally, obviously, the server will receive this packet. It will receive this retransmission. Again, the server is happy because it goes, well, the sequence number in this packet ends E23. I've already acknowledged that, so I can drop that packet. I don't need to do anything with it. But again, the same as last time, it will retransmit that acknowledgement. But it won't transmit the acknowledgement ending E28 as it did originally for that packet. Remember, the acknowledgement number is what have I got up to, and I have got up to as a receiving host up to the number E2B. So that's what it will transmit back here. So the client will get a duplicate ACK. They'll get two ACK packets with the same acknowledgement number, a duplicate ACK. But again, that's fine from the service point of view. It's just reconfirming that everything has been received correctly. So there's no errors here. There's no kind of uncertainty here. So duplicate ACKs aren't always a bad thing. They're just a sign that your network is working correctly. The final scenario to look at is on optimization. And within TCP, we have a fast retransmit optimization. So imagine the scenario where our client will be sending 4 packets to the server. Previously, we looked at examples where acknowledgements were lost, but obviously the data from the client those packets can equally be lost, corrupted, whilst they're being transmitted. So in this scenario here, the client sends 4 packets of varying sizes with obviously incrementing sequence numbers, and they will be transmitted to the server. So the first one is received okay, and it will send back an ACK. The second one, this packet here, is lost. It never gets to the server. But the third and the fourth do. So they will be received and acknowledged. Now the server can detect that something has gone wrong. See, it will receive a sequence number starting 23. So it knows that the next packet should be starting 28, but it doesn't get that one. The next packet it gets is starting E2B. So it knows that something has gone wrong. It knows that a packet has been lost or delayed. So remember, the acknowledgement number sent back to the client is a byte count of where I've got up to in this string of segments. What byte count have I got up to in that block of data that you're sending me? So for this first one, it'll send back the acknowledgement saying I've got everything up to E28. So it'll send that one there. It receives correctly this packet. So normally it would send back an acknowledgement with an acknowledgement number ending E2E, but it hasn't got a continuous block of data to that point. It's missing a chunk. So the acknowledgement number going back will be what have I got up to? Not what have I received, what in this block of data have I got up to? And I've got up to E28. Then there was a gap, and I want that data before I can continue. So on receiving these packets here, the server has a choice. You can either just dump them and go, right, I'm not going to do anything until I get this sequence number. So everything else you'll send me, I will not record and force you to retransmit. But yeah, that's perhaps a little bit non-optimal. So typically what we'll do is we'll hold these ones back in our buffers in the hope that this one will be retransmitted, and then within the server we will have all the segments we need to be passed up to the application layer. But it very much depends on your system. Obviously, if it's a normal server, you've got infinite. You've got a lot of memory, so buffering stuff, holding stuff is not a problem. But if you've got a small embedded device, maybe you've got a memory constrained device, yeah, perhaps you don't want to, or perhaps you can't store an awful lot of data on your system. But anyway, from the server's point of view, for each packet it successfully receives, it will transmit back an acknowledgement. So let's send back an acknowledgement for the first packet, third and the fourth. But again, as I was saying, the acknowledgement number it's sent back for these two here will be the byte count, what I've got up to, so ending E28. So again, the client will receive duplicate ACKs. It will receive 3 ACK packets with the same acknowledgement number. And from that, it can go, ooh, I can see that the server is telling me it hasn't received a packet with a sequence number starting E28, this packet here. So even though a timeout has not occurred, because it's received 3 duplicate ACKs with the same acknowledgement number, that will force a retransmission. So it'll retransmit this packet. It won't wait for that timeout. So you can again imagine if it was that initial communication process, the timeout will be 1 second. It's obviously a lot more efficient when the client realizes that something's gone wrong, not to wait for the timeout, retransmit that packet as soon as possible to maximize your communication efficiency. And that's what it will do. There you go. So it's retransmitted it now, and the world is good. Rightio, so some things to consider from those sequence diagrams. So if you go back to the previous one here, you can see here the client is not waiting for an ACK to come back before it transmits the next segment. So what that means is that you can have multiple packets in flight before you know if the server has received them. So we know the end-to-end delay, the latency between 2 hosts on a network, is given by the number of hops, number of stages, and each stage is the processing delay, queuing delay, transmission delay, and propagation delay. So as this question here is hinting, so if your communication latency is large, as it would be going to Australia, so hundreds of milliseconds, and you're pushing packets onto the network at your end quite quickly, you will have effectively multiple packets in flight at the same time. So if you consider this example here, how many would you have? So to simplify that, what we're going to say is it's going to be just one piece of wire. So we've got one wire from one end to the other, and we're the only person using that network. So there's no processing delay or queuing delay because there's no routers, no switches in between. So it just boils down to now the transmission delay and the propagation delay. So that will be 8,000 bits. So our transmission delay is given by that bit rate, how quickly we can squidge those 8,000 bits out of our NIC. And we can make some assumptions about the propagation delay, how long that cable is. You can say it's, around about 125 milliseconds to get to Australia. Obviously, that's very dependent on how your packet is routed across the world, but just for these back of the envelope kind of calculations. So if you kind of do that, and sit down and think about that one, you're kind of looking around about 20 segments can be in flight at any one time. Well, that might not sound so bad, but we're running quite slow here. So if we went to 10 megabits, 100 megabits, gigabits, then suddenly you can see you can get 1 or 2 packets stored on that wire, stored in flight. So that now there's a possibility that you can start to overwhelm your receiving host. Suddenly it'll get thousands of packets suddenly descending upon it that it has to process. So we need some way of implementing flow control. We need some way of coordinating how fast the transmitter pushes packets onto the network, depending on how quickly the receiving host can process them. Because if we send too many too quickly, those packets will overflow perhaps the receiving host's queuing buffer. So it's only got a finite space to store incoming packets. When that becomes full, it'll just start dropping packets. And if it drops packets, that will obviously trigger timeouts and retransmissions on our transmitting host. So things will start to slow down. So when you want to avoid that scenario, we want to send the data from the transmitting host at a speed that the receiving host can process them comfortably. And we can do that in TCP. Okay then, the first thing we need to agree is how much data we'll be sending each time. So how big are those segments going to be? As the receiving host will need to buffer one or more of these. So this is what is identified in the three-way handshake. So remember that initial SYN, SYN-ACK, ACK communication process used to set up that TCP link. Within that, within the option fields, within the SYN packets, each host specifies the maximum segment size it's willing to take. So if it doesn't, it will default to the default value, which is around about 536 bytes, which obviously is a little bit on the small side. So typically you'll find that most hosts will accept something in the range of 1,500 bytes. As you can see here in this example, the option field here from our previous example is 1,460 bytes. From the client, so the client saying how big a packet am I happy to take, and equally in the SYN-ACK pack back from the server, it specifies the size it's happy to take. Now this is not a negotiation, this is a statement. It's saying I'm happy to take segments up to this size or smaller. Okay then, so we'll be communicating packets of that size, and they'll be received on the receiving host and pushed into the received buffer. So we'll allocate a queue, a buffer on the transmitting and receiving machines, and that will be filled up as packets come in. So it gives you that little bit of flexibility so you can handle any sudden peaks. So this raises the question, how big should this RX buffer be? So how much space should you reserve for each TCP connection on the receiving and transmitting machines? One rule of thumb to determine that is the bandwidth delay product. So how quickly can I squidge data onto the network, and what is the RTT time? So how long does it take to send a packet from the host, from the client to the server and get a response back? So if it's on your local network, typically that'll be running gigabit links. And as we saw in the lab, if you were pinging the Raspberry Pis from the PC, your RTT is around about a millisecond. So if you time those two numbers together, you get around about 125k bytes worth of buffer size. But obviously, as your RTT starts to increase, you will typically increase the size of that buffer because you will have more packets in flight. So we have our RX buffer, our received buffer on our server. So the client's transmitting data to that. So that will be stored in the buffer. The buffer can absorb some of those transient spikes in load. But we need to communicate back to the transmitting host how much space is available in that buffer. So as space starts to get used up, the transmitting host can now detect that. If we can send back the receive window size, and it can start to throttle back its transmission speed if that receive window, that free capacity in the buffer, is starting to be used up. So this RX window will be your buffer size minus the amount of data in that buffer. So the last byte received minus the last byte read from that queue. So think of that as the sequence numbers, obviously because the sequence number is the byte count of that data stream. So from the transmitting host's point of view, if the receiving host sends back this RX window size, the amount of free space in its buffer, to the transmitting machine, it can work out how many bytes it can safely put onto the wire, how many bytes can be in flight, because that will be the RX window minus the sequence number of the last byte sent minus the acknowledgement number back from the server, because obviously that will give you the number of bytes in flight. So this number here, you always want to be less than this number. You always want to have free capacity in your buffer to absorb incoming packets. So that's what we do have. We have that in our TCP header. So if you look here in your TCP header, every time you send back an ACK packet from the server, acknowledgement the reception of new data, a new segment, it will send back its current received window size. It will send back how many bytes it's got left in its received buffer. Now some of you are probably shouting out already, hang on a minute. This is a 16-bit field, so this number here can only be up to around about 64K, and you've already specified that a minimum kind of RX buffer size is around about 125K, which is a lot bigger than 64K. So how can you specify the amount of free space if you've only got a 16-bit field? So to allow TCP to support those larger buffer sizes, we get window scaling. So again, within those three-way handshakes, those initial SYN packets, each machine will specify a scaling factor. So a multiplier to that 16-bit value. So you'll take that 16-bit value, and in this case here, if we look at this packet capture, we can see the scaling factor is 7. So that's not times 7, it's 2 to the 7. So you would multiply your 16-bit value by 128, and obviously using that we can specify very large windows indeed. We can specify very large buffer sizes. So as we saw previously with a normal TCP communication, you'll have perhaps your client sending the server some data, so send packets. So you can see some data packets being transmitted in this example here. So here we have a machine ending 101.5. transmitting data to the server ending 101.9, and you can see that these are data packets basically because of the size, so they're full MSS size packets. So you've got 1460 bytes worth of data plus your headers, so your TCP header, your IP header, all the stuff that is used to encapsulate that packet, and that gives you finally 1514 bytes worth of packet. And that has been sent to the server. And again, you can confirm your suspicions. Obviously, this one also has the push flag set, sending that this data should be pushed up to the application layer. But in general, if you see big packets like this, full MSS size packets, these are transferring data. You can identify your ACK packets coming back the other way. Obviously, you can see it's coming from the server to the client now. Obviously, data goes from the client to the server. And the size, you can see these are small packets. They're 66 bytes in size. So these are acknowledgement packets for previously received data. And within that packet will be your RX window size. So in this particular one, it's 501. But that 16-bit value is then multiplied by 128 to give your calculated window size. So the actual amount of free space, the free number of bytes that are available in your receiving machine. So the TX machine knows not to send more than that. So it can push out onto the wire bytes up to that calculated window size, because it doesn't want to fill up that buffer, risk overflowing that buffer, risk packets being dropped at the received end, which will trigger retransmissions and timeouts. So demo time. So in the lecture review session, we'll go through some demos, we'll transmit some packets onto the network, and we can also see graphically the RX window size by using TCP trace, so a graphical representation of the data being transmitted, the acknowledgements, and the size of the RX window. So the gap here is indicating how many bytes are left in that RX window. So you have time on your x-axis, and you have sequence numbers or byte count numbers on your y-axis. And these are a good way of analysing, a good way of observing how your network's behaving. Sometimes it gets a little bit overwhelming when you look at the full packet trace. You can see here, you don't get a chance to step back and see actually what's actually happening over a period of time, which a TCP trace does allow you to do. So again, we can see these blocks here showing when data is transmitted a certain amount of time later, normally RTT time span. You'll get acknowledgements. The steps you're seeing here are acknowledgements to the received data. And again, the gap between here and this line at the top here indicates your receive window size. So you never want the transmit data values to kind of run into this hard limit. So if you have data being transmitted and it touches this top line, then you're in danger of overflowing your RX buffer. Again, just to point some key bits out here. So here, each one of these little black bars here is a MSS size packet being transmitted. These can be acknowledged individually, and that's why we have this little staircase going on here. So each step up is acknowledging one of those packets being received. But you can have cumulative acts, and that's what you can see here. So you can see this is the byte count that has been acknowledged so far, and it remains steady, and then suddenly jumps up, acknowledging all of these packets in one go. So yeah, it's more efficient. You've got less little packets being transmitted around the network. As I was saying, if we add some delays in our processing, eventually your RX buffer will overflow, and you'll see an error message being reported in Wireshark. You've got zero capacity in your RX window. So if you look here, you can see that the transmitting and the gap between that previously top line and the top of your data is disappeared. So now it's hitting that limit, and that's the point you can see here. So the difference between this top line and where your data is on that moment in time indicates how much space you've got in that received buffer. And as we can see here, because it's hit the top there, we've got none. We get this error message. There's no capacity left. So Wireshark has detected that there's enough bytes in flight to fill up that received window. So this is flagging it to you now that something bad is going to happen unless that receiving host can push up to the application layer some of that received buffer to free up some of that space so that it can receive more data. But eventually, in some scenarios, you will get to that point where that received buffer is just full and it can't take any more. So you'll see an ACK packet, as you can see here, with a true zero advertised. Remember, this number here, the window size coming back to the transmitting machine from the server, the receiving machine, says how much data it can receive, and it's full. So the transmitting machine will have to stop sending data. And we'll look at that one and talk about more of that one in that demo in the lecture review session. Okay, so up to this point, let's have a little pause to consider what we've seen. So we can see that TCP can handle the fault scenarios. So if packets go missing by a combination of timeouts, sequence numbers, acknowledgement numbers, we can work out what packets have gone missing and ask for retransmissions. So that's all good. Equally, we've got some flow control using that receive window size. So we can pump data into our system and detect when our server can't keep up. So going back to that initial problem we had, that quick quiz, we saw this system here where we've got a server and we have a bottleneck. We only have a 20 megabit per second link to the server from the last switch, which, as we saw, will introduce that flow control problem. So obviously data could be pumped into this network far faster than it can go out. So we could have all three client machines here connecting to the one server. So in theory, they could be pumping in 120 megabits per second into the system, and obviously that has to squeeze through this 20 megabits link. So we need flow control, and we saw how we could do that with the server sending back to each of these clients its receive window for each of the three buffers that it would have, such that the clients could throttle their transmissions, could slow down, reduce the amount of data they're sending, such that they didn't overflow those RX buffers. Okay, so far so good, but what happens if there was just too much traffic in the network? So typically your communications will be bursty in nature, but let's say this machine here continually streams data to that machine. So fundamentally there's just too much data coming through. So these machines here would be effectively disconnected from the network because this one machine is hogging all the bandwidth to the server rather than taking its fair share. So how can we handle that in TCP? How can we handle the network hogs in our system? And we do that with another window. We do that with the congestion window, the congestion control window. So again, there's no direct way of measuring how much data is on the network. We don't sort of interrogate the switches to say, how busy are you? But we can infer how busy it is by the number of lost packets. So if we go back to this scenario here, so imagine this switch here. So these machines are pumping data into our network and they're being funneled through this 100 megabits per second link. So this data will be received into this machine here. So its received buffer for that port will start to fill up because the data coming out of this switch is coming out at half the speed. So eventually the received buffer in this switch will be filled up. So any new packets coming in will just be dropped. There's no space for them to be stored. Remember, this is store and forward. It's a packet switch network. These packets will be lost. So therefore, the transmitting machine will not get back an acknowledgement because those packets will never get to the server. And that's what it can use to detect congestion. So if it starts to detect that it's not getting back these acknowledgements, then there's probably a good reason for that, and it's probably down to the amount of traffic on the network. So what we can do is we can define a congestion window. We can define the number of unacknowledged packets that we're happy to have. And we can use that to determine how many bytes we're happy to have in flight at any one time. And obviously this is not standing alone. This has to be integrated into our flow control mechanisms. And that's what you're seeing here. So the number of bytes in flight is whatever is the smallest. So it's either our RX window, so how many bytes can our receiving machine buffer, or how many bytes are we happy to have unacknowledged in flight, whatever is the smallest. So the number of bytes in flight, as we saw previously when we looked at the buffer, is given by the sequence and acknowledged numbers. So the last sequence number transmitted minus the last acknowledgement number received, because obviously these are our byte counts. If we assume memory is cheap, then obviously we can put a big receive buffer, so infinite buffering is available. Obviously there's limits. You're looking at around about a gigabyte or so, which is quite a bit of memory. But if we assume that, then it all boils down then to our congestion window size. So we get back to those bandwidth delay product type calculations, so we can see that our transmitting speed is now given by the congestion window size in bytes divided by our RTT. So to start off with, what size of congestion window should we use? How many bytes should we have out on our wire without being acknowledged? And we start off conservatively. We start off expecting the worst, so we start off with just one MSS packet's worth of stuff going out on that wire, and as we saw from the previous examples, roughly 1500 bytes. So all of this, our congestion control algorithm, is defined in RFC 5681, so do have a look at that link. But basically it's boiled down into three main elements: a slow start, congestion avoidance, and fast recovery. So as we identified, to start off with, we're going to start slow. We're going to start our congestion window off with one MSS packet in flight. And then each time we get an acknowledgement, we'll increase that by 1. So we get this exponential rise in packets in flight. So we start off with 1, get the ACK, we'll double our congestion window to 2, so then we'll receive 2 ACKs back, so then it goes to 4, then 8, then 16, so you can see we're going to get this increase in speed. So what we're doing here is we're probing the network. We're kind of increasing the amount of traffic we're pushing onto that network until we start to lose packets, until we don't get an ACK back, and until we get a timeout, or until we get that 3 duplicate ACKs coming back, which would trigger a fast retransmit. So all of those sort of indicate that we're starting to lose packets, that we're starting to send too much data onto that network. When we detect that scenario, we set that slow start threshold to be the congestion window divided by 2. Kind of identified where it starts to get lost, so a safe value will be half that value. Then we reset our congestion window to 1, and we switch to congestion avoidance. In addition to that, as I was saying, we have this slow start threshold, and that's set to some predetermined value. So you're transmitting data onto that network, the amount of packets you'll have in flight will exponentially grow, but you can't continue that process forever because obviously there'll be a maximum limit. And obviously you don't want to cause self-inflicted congestion. So you reach a point, your slow start threshold, where you stop that process. So let's say it's 64 packets. But it could be larger, but you reach a limit where you go, right, I'm not going to continue to exponentially increase the number of packets in flight. I'm going to switch now to congestion avoidance mode. So in this mode, we're starting off with our congestion window half that where problems were detected. And now it's incremented by 1 when we receive back all the ACKs for that congestion window. So rather than exponentially incrementing now, it'll be a linear increase. So a gradual increase. And again, that will continue until we get some timeouts, until we start to lose some packets. As it says here, both for the slow start and the congestion avoidance modes, we'll use that 3 duplicate ACKs to determine if we've got a lost packet. But this time we will switch to the fast recovery mode. So because we're still getting ACKs back, we don't go for such a doom and gloom mode of operation. We set for a slightly bigger congestion window size. And again, as I say, because we are getting ACKs back, then that shows that the communication link is working. If we just don't get anything back, then packets are being dropped, are being lost. But if we're getting duplicate ACKs back, that's a good sign that we've still got capacity in our network. However, if timeouts start to occur, we'll switch back to that soft start or switch back into our congestion avoidance mode. So what that means is you start to see stuff like this. Well, probably not things exactly like this, not like this badly drawn diagram, but things like this. So initially we have this slow start, so we'll exponentially be increasing the packets on our network. Then that crosses our slow start threshold. So the next one we don't double, we just linearly increase it, adding 1 each time we get back all our ACKs. But again, at some point, we'll start to lose packets, we'll start to get timeouts. So again, that will crash back down, and again, exponentially rise up again until we cross that threshold. Now, how this congestion control algorithm works, there are some variants in this one, so do have a read of RFC 5681. So how you adjust that congestion window size. Do you go back down to 1 MSS and start from the beginning again, or do you switch to some intermediate value? As I say, there's some variations in there, so do have a look at those. But hopefully that gives you a flavour of what we're looking at. Now, I do confess I was trying to set up a demo to show congestion control and action, capture a nice Wireshark TCP trace, but in reality it's quite a hard one to set up because obviously you have to lose acknowledgement, you have to lose packets. So you end up with a really messy trace, to be honest. So this one here doesn't really show congestion control, but does show the slow start. So we're going to take that one as a win. So you can see here we've got a TCP communication in process. So this is our acknowledgements coming up. These little blue ones are the data being transmitted. And the gap between the acknowledgements and this top trace here is your receive window. So as you can see here, we're transmitting data and eventually we fill it up. But at the beginning, we can see this slow start. So we're starting off actually with 2, then 4, then 8, then 16. We're filling up that buffer and then it'll start to do some flow control here and start to throttle it back as that buffer is not being emptied. So not really showing congestion control on that one, but showing one of the modes within that congestion control mechanism. So finish things up. So TCP, reliable protocol. So we set up that communication link from the transport layer in one host to the transport layer in another host, and it's used in a lot of protocols where you need to ensure that reliable communication. So Telnet, SSH, FTP, you name it, they tend to use TCP. And as it says there, it's the one of the founding members of what is the internet. So the TCP IP, the IP one will be seen in 2 ticks, are the fundamental protocols used out there on the internet. But obviously having that reliable communication link does come at a cost. You need additional fields in your TCP header, as we saw, sequence numbers, acknowledgement numbers, receive window size, and quite a few more optional ones as well, if truth be told. In addition to that, because we have to handle retransmissions, etc., then obviously there's a lot more state information needed for each TCP connection that you don't have for UDP. And again, we need buffers that we don't have necessarily with UDP. So if we are transmitting stuff, we need to buffer that packet just in case we need to retransmit it. UDP, we don't. We just send that onto the wire. There's no retransmission if that packet was to get lost. So I know it's confusing, but do take your time to think about the sequence and acknowledgement numbers. To some degree, they're a simple thing to understand. They're just a byte count of what data are sent down this TCP stream. But working out how they change in reality in that Wireshark trace does take some thought. So do step slowly, don't rush it, do think about those numbers and what you're actually seeing in the labs, because it does get confusing rather quickly. And we'll be looking at all these different things as we go through our lab. So timeouts, the various flags, so SYN, SYNAC, push, reset and fin, three-way handshakes, window sizes, all of that good stuff. We'll be looking at examples in the labs, on the Raspberry Pis and the PC using Wireshark. So again, to repeat what I said just previously, if you're finding TCP difficult to understand, that's because it is. And to make things even worse, we've only scratched the surface. So yep, background reading, have a look at those RFCs, have a ponder, have a look at other documentation and videos out there on the net. It does take a while to think about what's going on and to understand what's happening under the bonnet there. Okay, so that's the end of our transport layer. So now we're going to step down to the network layer and look about how we actually connect 2 hosts together, because obviously with TCP and UDP, we're dealing with ports, so communication between 2 ports effectively, but we're not really thinking about how we actually get the packets from one machine to the other. So how do we route those packets across the internet? How do we know how to get from point A to point B? Because this isn't a circuit switch network. We're not forming that connection at the beginning and we just pump packets into there and the connection is made, we need something to route the packets across the internet. And as you probably guessed, that's our network layer, that's our IP protocol. And that's what we'll be looking at next time. So that's where we're going to leave it for the moment. And as always, I will see you next week.